Welcome back, guys. This video is about chain rules. In this video, we're going to focus on chain rules involving a single independent variable t. So we'll have three cases. We'll have z given by a function of x and y. If we replace each x with x of t and each y with y of t, then we end up with a new function. All the x's are gone. They've been replaced with some expression involving t. And all the y's are gone. So they have been replaced with some expression involving t. So now f depends entirely on t, and we can ask about its derivative with respect to time, or derivative with respect to t. This is very similar. If w depends on x, y, and z, and x, y, and z are all functions of t, well, then my new function, w, after I take a composition, will depend entirely on t. I'm replacing x with x of t, y with y of t, and z with z of t. And I won't write this one out, but this is very similar. If I have a function of n variables, x sub 1 through x sub n, and it turns out x sub 1 through x sub n all depend on t. So maybe those are the parametric equations of some vector-valued function in n-dimensional space. Well, if I replace x1 with x1 of t, x2 with x2 of t, x sub n with x sub n of t for every component, then this new function depends entirely on t. So in this video, we're going to write down chain rules for each of these cases that will allow us to find the derivative of z, w, or that other w with respect to t. And we're going to express those chain rules in two ways for each of the three cases. For each case, we will describe or define the chain rule in terms of derivatives and partial derivatives. Partial derivatives of this function and ordinary derivative of these functions over here. And we multiply them together and add them in certain combinations to get a chain rule. And then we're also going to write that much more compactly as a dot product involving the gradient and the derivative of a vector-valued function like this. So that's what's coming. But before we start doing that, I'd just like to review the chain rule from Calculus 1. In Calculus 1, remember how the chain rule worked. You had a composition of functions. You're trying to take the derivative of f of g of x. And most of the time, this is how it's written. And we said in Calculus 1, if you want the derivative of f of g of x, first you take the derivative of the outside function, and you evaluate it at the inside function, and then you multiply by the derivative of the inside. So you have the derivative of the outside. I'm just writing this out in words for you. So that's the derivative of the outside function, that's f prime, evaluated at the inside function, so you just plug that inside function back in. Don't take its derivative yet, just substitute it back in, and then you multiply by the derivative of the inside. And I've heard many people skip this part. They'll say just derivative of the outside times derivative of the inside. Easy breezy. That's right, but you have to be careful. It's the derivative of the outside evaluated at the inside, so you have to put that inside function back in. So that's normally how it's stated, using prime notation. Now we could also state this derivative, this chain rule, using Leibniz notation. And the Leibniz notation means exactly the same thing, but it's written in a slightly different form. So let's say that y is a function of u. And then u is some function of x. Well, if I take a composition of these two functions, if I put them together, I'm replacing u with u of x. Now all the u's will be gone because all the u's have been replaced by these functions of x, these expressions involving x. So now y depends on x. Here's the Leibniz notation for the derivative of y with respect to x, because y now depends on x. The derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. Now this is just a regular multiplication that's not a dot product because neither of these are vectors. Now this looks different from this, but it's exactly the same thing. This is the chain rule and this is the chain rule. It's just written in a slightly different form. Here, y is the outside function. We have y equals f of u, or we could have just said y equals y of u, and that would have been fine. So y is the outside, and what we're saying is take the derivative of the outside function, plug the inside function back in. It's f prime evaluated at the inside function. It's g of x here, or u of x here, times the derivative of the inside. Derivative of u of x can be written du dx using Leibniz notation. So this is exactly the same thing. And you have been computing, or you have been using the chain rule, the calculus 1 chain rule, when you were taking your partial derivatives. So hopefully this is not new to you, because you've been doing this in the last few homework assignments. It's the derivative of the outside evaluated at the inside times the derivative of the inside. Now, just as an example, just so that we have one concrete example of this, let's say that y is equal to trying to think of a composite function. Let's do y equals the square root of x cubed plus 5x. Well, if I want to take the derivative of that, I would probably use this notation. I notice that I've got a function nested inside another function, so it's a composition of functions, so I know I'm going to have to use the chain rule. So the first thing I would do is rewrite it. A square root is the same as the 1/2 power. It's that power over that, or it's that over that. That implied exponent was a 1. The index of the root goes in the denominator. If I want the derivative of this, I apply the chain rule. So first I take the derivative of the outside function. Now the inside function needs to be identified. That's all of this. Now, your inside function is usually a function nested inside another function. If there are parentheses, the inside function is usually in the parentheses. If there's a radical, it's usually under the radical. If there's a trig function, it's inside the trig function. If there's an exponent, it's in the exponent, like an exponential, like e to some power. But here I see the parentheses. I say I'm taking all of this and I'm raising it to the 1/2. That's my inside function. Well, according to the chain rule, the derivative is derivative of the outside. What's the derivative of a function to the 1/2 power? Well, it's 1/2 of that function to the 1 less power. And then you substitute your inside function back in. So don't change it yet, just plug it back in. And then multiply by the derivative of the inside. So that's a Calc 1 chain rule. Derivative of the inside is just 3x squared, because I'm bringing my power down, multiplying by x to the 1 less power. And then I'm adding a constant, the derivative of a constant times x. The derivative of a constant times x is just my constant. So by the chain rule, this is 1/2 times the quantity, 3x squared plus 5. All of that times this quantity to the negative 1/2. If you prefer, you can write that in the denominator under a radical, that's fine. But that's just the Calc 1 chain rule. Okay, so now let's talk about these three cases, the Calc 3 chain rules, or at least Calc 3 chain rules for a single independent variable t. So we're replacing x with x of t, and we're replacing y with y of t. Well, that's a composite function. I've got two functions nested inside of another function, so I'm going to have to use the chain rule. Now, if I know what x of t and y of t are, I could just plug them in and take the derivative with respect to t. So we will do that as well and show that you can get exactly the same result using that technique. But the chain rule itself is important because it allows us to derive other facts. We actually use the chain rule to come up with the equation for the tangent plane in the next section. So it's really important, even if there's often an easier way to compute this derivative of z with respect to t. Okay, so with that in mind, let's look at an example. So this is our first Calculus 3 example involving the chain rule. So let's say that z is given by x squared times y, and x is e to the 3t, and y is e to the negative t. If you put these pieces together, replacing x with e to the 3t and replacing y with e to the negative t, z is now a function of t. So z is x squared times y, and x can be replaced by e to the 3t, and y can be replaced by e to the negative t. Now, using exponent properties, I can simplify this, and then I can just differentiate the function. That's going to give me the derivative of z with respect to t. Now, here are some exponent properties that we might need here. Remember, if you take x to a power and you raise it to a power, you just multiply those exponents. We're doing exactly the same thing here, it just looks different because of the exponential. I'd multiply the 3t and the 2, so that's going to give me an e to the 6t. And here I've got two exponentials that are multiplying each other. Remember, if you take x to some power times x to a different power, the bases are the same, so you just add the exponents. The same is true here. The bases are the same, we add the exponents. 6t plus negative t is 5t. So z is e to the 5t. If I want to take the derivative of z with respect to t, and I'm going to use Leibniz notation because we're going to use it so often here. Just taking the derivative with respect to t of e to the 5t. Well, that requires the chain rule. Chain rule for functions of one variable. Here's my inside function. First we take the derivative of the outside. Derivative of e to some power is e to that power. You just write down the exponential again, don't change it. And then you multiply by the derivative of the inside. And of course the derivative of 5t is just 5. So we end up with 5 times e to the 5t. And that's dz dt. So that's one way of finding dz dt. Now I'm going to show you another way, and you're going to say, why on earth would I ever do that? Why can't I just substitute and do this every time? You're right, you could just substitute and do this every time. But it's very important that we understand how the chain rule works so that we can use it to derive other formulas and facts. So now I'd like to show you that we get exactly the same answer. We get 5 times e to the 5t using the Calculus 3 chain rule for functions of two variables. So here's the Calculus 3 chain rule for functions of two variables. Or here's one version of it. So we're given z equals f of xy and x equals x of t and y equals y of t. If that's true, then it turns out, under certain conditions about differentiability and all that jazz, the derivative of z with respect to t, and this is an ordinary derivative, it's not a partial derivative, because after we take the composition, f depends only on t. This derivative is the partial of z with respect to x times dx dt. This is going to give me the change in z as x changes with respect to time, with respect to t. So if x is changing by a little bit, the z is going to change accordingly. And then if x is changing as time is changing, you multiply those two together and you get the change in z with respect to t due to the change in x. Let me write it that way. This is the change in z with respect to t due to the change in x. X is changing a bit. Because x is changing a bit with time, z changes a bit because of the partial of z with respect to x. All those are related. Now that is not going to give me the entire derivative of z with respect to t. Z depended on two variables, x and y. It turns out if your function depends on two variables, you're going to have two terms in your chain rule. We've got the change in z with respect to t due to changes in x, and then we're going to add the change in z with respect to t due to changes in y. Okay. Now, in order to use this chain rule, I need to take those two derivatives. Now, those are just ordinary derivatives because x and y depend only on t. There's only one independent variable, so that's just a regular derivative. And we call regular derivatives ordinary derivatives. These partials of z with respect to x and y are partials because z depends on two variables. At least before the composition, z depended on x and y before. So I get a partial of z with respect to x and a partial of z with respect to y. Now all of this needs to be written in terms of t to get dz dt. So you might find the partial of z with respect to x, and then write it in terms of t by replacing x with x of t and y with y of t. And you'll find the partial of z with respect to y, and you want to write that in terms of t by replacing x with x of t and y with y of t. So this is one version of the chain rule. This is one of our three cases. Everything is written in terms of t. Now, another way of saying exactly the same thing is to call this a dot product. You can say the dot product of what? Well, look at these components, guys. Look at all these things that we're multiplying together. I'm taking the partial of z with respect to x and the partial of z with respect to y. Those are the components of the gradient vector. And I'm multiplying them by these two guys. A partial of, or the derivative of x with respect to t and the derivative of y with respect to t. Now that looks familiar too. Now, I can think of this as a dot product if I write this just a little bit differently. So if x is equal to x of t and y is equal to y of t, I could think of those as parametric equations for some vector valued function r of t. So r has components x of t and y of t. And then this is the gradient of f, and I'm taking that and I'm dotting it with not r, but the derivative of r. So another way of stating this is to say dz dt is the gradient of capital F evaluated at x of t, y of t. So you take the partial of f with respect to x, partial of z with respect to x, same thing. Take the partial of f with respect to y, partial of z with respect to y, same thing. And you replace the x with x of t and the y with y of t. And you're going to have a vector right here. And then you're dotting that with r prime of t, where this is r of t. So this is the other version of the chain rule. And this actually looks a lot more like what we're used to seeing. I don't like this notation because it does not make it clear how many components f originally, or how many variables f originally had, but sometimes you'll see this chain rule written this way. The gradient of f evaluated at r of t, where you take the components x of t, y of t, and you substitute those into in for x and y here, dotted with r prime of t. And this looks a lot like our regular ordinary chain rule. It looks like we're taking the derivative of the outside function and evaluating it at the inside function, r of t, and then multiplying it by the derivative of the inside. So some people like this better because it just looks a lot more like the calculus 1 chain rule. I really don't like doing this because, yeah, it just doesn't indicate how many variables we have over here in this gradient vector. I actually can't even tell, the length of this vector or the length of this vector from this equation, which might be nice. I mean, maybe this is the version of this equation that works for 2 components, 3 components, n components. This is going to be the same for all 3 cases that we're going to look at today. So this is another way of saying the same thing, just in terms of a dot product involving the gradient. We're just saying this more compactly. We're saying it with a more compact equation. Okay, so we had that example earlier. We know what the answer is. Let's do it using the chain rule. So this is our first example, revisited. We were given z equals x squared times y, and x was e to the 3t and y was e to the negative t. Okay, well, I'm going to do this example 1 2 different ways. I'm going to do it using this formula, and then I'm going to do it using this formula. And we're going to see whether we immediately make the substitution and differentiate, or use this formula, or use this formula. We're going to get exactly the same answer. So first, let's use this formula. So what I need is the partial of z with respect to x and the partial of z with respect to y. I need the derivative of x with respect to t, derivative of y with respect to t. I need both of those partials written in terms of t, and then I need to multiply everything together. So using this formula. So I'm just going to make a note to myself. Method number 1, we're using that starred formula. The first thing we'll do is compute the partials of z with respect to x and y. So you can write it this way if you want, or you can write it using subscript notation, that's fine. But you're going to compute those partials. With respect to x and y. And because it's more compact, it's easier and faster to write. I'm going to use subscript notation over here. We want those two partials, and remember we want them eventually in terms of t, because I want everything here in terms of t. I want this derivative of z with respect to t to only have t's in it. Oops, written in terms of t. Okay. Derivative of this with respect to x. Remember, y is a constant, so you bring your constant down. Derivative of x squared with respect to x is just 2 times x to the first. Here I've got a constant times y, because I'm treating x as a constant and y as my variable. The derivative of a constant times y is just my constant. So those are our two partials, but right now they're written in terms of x and y, so I need them in terms of t. So I replace x with e to the 3t, and I replace y with e to the negative t. So I'm replacing x here with e to the 3t, and then I'm squaring it. Okay, so those are our answers. I'm going to simplify a little bit more. The partial of z with respect to x is this. Using exponent properties, I have 2 times e to this power times e to that power. Add the exponents, it's going to be e to the 2t. 3t plus negative t is 2t. Partial of z with respect to y, I'm taking this and I'm squaring it. So I multiply those exponents. Remember how that works? X to the n to the m, we multiply the exponents. This is the same, it's just a different base. So I've got e to the 3t squared is e to the 3t times 2, so e to the 6t. 3t times 2 is 6t. So we wanted those two partials in terms of, written in terms of t, and we've got them. Okay, that was our first step. Second step is to find the derivative of x with respect to t and the derivative of y with respect to t. And I'm going to use prime notation here. Now, there are all these different notations for derivatives. We have to be comfortable with all of them. So dx dt, or if you prefer x prime because it's shorter, that's the derivative with respect to t of x, whatever x was. And remember, x was e to the 3t, so I'm substituting that here. And I need the derivative of y with respect to t, or we could call that y prime of t, same thing. So we're taking the derivative with respect to t of e to the negative t. The derivative of e to some power is e to that power times the derivative of the inside by the chain rule. It's not 3t, the derivative of 3t. The derivative of the inside is a 3. Derivative of e to the negative t is e to the negative t times the derivative of the inside. The derivative of negative t is negative 1. Okay? So we computed x prime and y prime. We computed those two partials, and now we want to put them all together. To find z prime of t, or dz dt, same thing. That was step 1, here's step 2, and here's step 3. dz dt is the partial of z with respect to x times dx dt. It's the change in z with respect to t due to changes in x, plus the change in z with respect to y, or the derivative of z with respect to y, partial derivative, times the derivative of y with respect to t, ordinary derivative. And then you're just substituting and simplifying. Well, the partial of z with respect to x was 2e to the 2t. Dx dt, that's x prime, same thing, is 3 e to the 3t. partial of z with respect to y was e to the 6t, and derivative of y with respect to t is negative e to the negative t. Using exponent properties, well, first we'll multiply the coefficients. 2 times 3 is 6. Then this guy times this guy, you add the exponents. That's e to the 2t plus 3t is e to the 5t. Here we have a 1 times a negative 1 is negative 1. Here, add the exponents. 6t plus negative t is 5t. If I've got 6 of these and I'm subtracting 1 of them, that means I've got 5 of them. That's my answer. That's z prime of t. I know that was long and involved, but isn't it the same answer that we got when we substituted earlier? Yes, it is. We had a 5e to the 5t using the ordinary chain rule after a substitution. I know this is much faster, but we want to make sure that we understand the chain rule and how it works when we use this method. Okay, so that's one way of doing it. Or we could use this form of the chain rule. You take the gradient of f, where z is f of x, y, and you evaluate it at x of t, y of t. And then you take the vector valued function r of t with components x and y, and you take its derivative. Derivative of that and derivative of that. When you take the dot product of these two guys, this guy is the partial of z with respect to x times I hat plus the partial of z with respect to y. This guy is the x prime times I hat plus y prime times j hat. So when I take the dot product of these guys, I just get that formula back. So we're going to get exactly the same answer using this formula that we did with this method, but this is more compact. So let's do it this way instead. Let's use the dot product version. So this is method number 2, same problem. Or I guess it's method number 3 because we already did it by just substituting. So we had z equals a function of 2 variables, x squared y, and x was e to the 3t, and y was e to the negative t. And when we use this version of the chain rule, we'll use x of t and y of t as the components of r of t. So x is e to the 3t, and y is e to the negative t. And those are the 2 components of some vector valued function r of t. So first I'll state my chain rule. We have dz dt is the gradient of f at x of t, y of t. So you replace x with x of t, you replace y with y of t, and then you dot it with r prime of t. So when I use this method, the first thing I need to do is compute the gradient and write it in terms of t. So here's my vector valued function, or excuse me, my function of several variables. This is a vector valued function. This is a function of 2 variables. And if I want its gradient, I compute those partials, partial of f with respect to x and partial of f with respect to y. Derivative of this with respect to x is 2x times y, because y is just a constant. The derivative of this with respect to y, if x is a constant, this is just a constant times y. The derivative of a constant times y is just the constant. And then I want these both of these in terms of t. X is e to the 3t, so I replace x with e to the 3t. Y is e to the negative t, so I substitute that in. Here, I replace x with e to the 3t, and then I square it. So using exponent properties, I get 2. Here you add the exponents, that's e to the 2t. I'm doing this a little faster this time because we've already done these calculations. Here I've got e to a power raised to a power, so we multiply the exponents. So our gradient function, it was 2xy times I hat plus x squared times j hat. In terms of t, that turns out to be 2e to the 2t and e to the 6t. So that's what we just found. Okay, that was this part. Now I need r prime of t. Well, r of t had components e to the 3t, e to the negative t. Computing r prime is easy. You just take the derivative of each component separately and then add them. Or excuse me, not add them. You take the derivative component by component, and the resulting vector is r prime. Derivative of e to some power is e to that power times the derivative of the inside, which is a 3. Derivative of e to this power is e to that power times the derivative of the inside, which is a -1. All right. Now we just take the dot product of those two guys. That's what our formula tells us to do. Last step. Compute dz dt, which is the dot product of the gradient evaluated at x of t, y of t, or if you prefer, you can just call it the gradient evaluated at r of t, dotted with r prime. So dz dt is this gradient dotted with r prime, which was 2t, or 2e to the t, or excuse me, 2 times e to the 2t times I hat, plus e to the 6t times j hat. That's my gradient. Here's my r prime. And I'm dotting these, so I just multiply component by component and add this times this. So it gives me 6 e to the 5t, and then I add this times this. Positive times a negative is going to be a negative. E to the 6t times e to the negative t. We add the exponents. It's that. I've got some like terms here. So the derivative is 5e to the 5t. Exactly the same thing we got with the other two methods. So whichever method you want is fine. But I want you to know that these are just two different ways of saying exactly the same thing. This is reminiscent of our calculus 1 derivative, or calculus 1 chain rule. It's almost the derivative of the outside evaluated at the inside times the derivative of the inside, but now whenever we're substituting something in, it's a vector valued function r of t, and that's not regular multiplication, that's a dot product. And that's not a regular derivative, it's a gradient. But it's the multidimensional analog of the first derivative, so it behaves the same way, or it behaves in a similar way to our first derivative. Okay, so that was one version of the chain rule. That was this guy. Now this one is very similar. The only difference is now you have a function of 3 variables. And you're replacing x with x of t, y with y of t, and z with z of t. Well, I think you can imagine what this new chain rule is. So if we're given that w depends on x, y, and z, and x, y, and z all depend on t, if I replace x, y, and z with these functions of t, I end up with an entirely new function of t. So I can take the derivative of that function of t with respect to t, and it'll have, since this has 3 variables, the chain rule will have three parts. It'll be the partial of w with respect to x times dx dt, plus the partial of w with respect to y times dy dt. And if this was a function of two variables, we would stop there. But there's also a z, so we take the partial of w with respect to z and multiply by dz dt. And of course we want all of these written in terms of t, because we want the derivative of w with respect to t to be a function of t only. Okay. And this is very similar. We can interpret each of these terms the same way that we did on the last one. This is the change in w with respect to t due to changes in x. And this is the change in w with respect to t due to changes in y. And then this is the change in w with respect to t due to changes in z. Now if this part doesn't quite make sense to you and you're like, I see what you're doing but I don't quite get it, I think it'll be clearer when we do some application problems. That will be in another video. For right now, just take my word for it. And then the shorthand version of this, well, it's pretty much the same thing that we did before. The partials of w with respect to x, y, and z, those form the components of the gradient vector. So this is the gradient of this function f, but we want to evaluate it at x of t, y of t, z of t, so that when we're done, this depends entirely on t. And then these guys, well, those are the components of r prime if r has components x of t, y of t, and z of t. So if we put these guys together in a vector valued function r of t, and I take its derivative, that's going to be x prime, y prime, z prime, and I dot it with the gradient, I get this. So this is the same as that. Or we can use that alternate shorthand, x of t, y of t, z of t is just the components of r of t. So this is our second version, our second case of the single variable chain rule. It's single variable because the new function depends entirely on t when we're done, because I replaced all the x's with x of t, y's with y of t, and z's with z of t. But since w originally had three components, x, y, and z, the chain rule has three terms. I don't even have to think about those three terms if I do this in terms of a dot product. I'll just take the gradient of w, which depends on three variables, so it will have three terms. And I take the derivative of r, which has three components, because it has an x, a y, and a z. I take those two vectors and I dot them. Okay, so that is the second case. Let's look at an example of this. Just a simple example. So let's say w is this function of three variables. Let's make it x times y times cosine of z. And maybe x is t, y is t squared, and z is the arc cosine of t. Okay. Well, we could do this problem 3 ways as well. We could just take the composition. We could replace the x with x of t, the y with y of t, and the z with z of t, and then compute the derivative that way. That's the easiest way. Or we can use those 2 versions of the chain rule that we just talked about. So let's use the very easiest way first. So we're going to substitute x equals x of t, y equals y of t, and z equals z of t, and then differentiate w with respect to t. Now, if I ask you to use the chain rule in a quiz, this does not count as using the chain rule. This is just one way that we can check our work. So w is a new function of x of t, y of t, and z of t. So it's x times y times cosine of whatever z is. And they told us what x of t, y of t, and z of t were, so we can substitute those in. X of t is just t. Y of t is t squared, and z of t is arc cosine of t. And the cosine of the arc cosine is just a t. So this is a t times t squared times another t. These are 4 t's multiplying each other, that's t to the 4th. Well, that's easy enough. If w equals t to the 4th, that implies that dw dt, or if you prefer w prime of t, same thing. It's the derivative of t to the 4th, that's 4t cubed. So we know that that's our answer. That's the easiest way to do that. Okay, whatever we do with the other 2 methods, we should get 4t cubed after simplifying. So let's use the other 2 methods. So we're going to use the expanded formula. W depended on 3 variables, so the the chain rule has 3 terms. You have the partial of w with respect to x times dx dt, plus the partial of w with respect to y times dy dt, plus the partial of w with respect to z times dz dt. And the first thing I will do is I will compute those 3 partial derivatives. So w sub x, w sub y, and w sub z, and write them in terms of t. Okay, so w was xy times cosine of z. Partial of w with respect to x, it's partial with respect to x of xy cosine of z. This is basically a constant times x, because remember, we're treating y and z as constants and we're differentiating with respect to x. The derivative of a constant times x is just the constant. So I'm just going to get that constant back, y cosine of z. But that's in terms of y and z. I want it in terms of t. So I need to replace y with t squared and z with arc cosine of t. So I've got y times cosine of z, and y was t squared, and we replace z with arc cosine of t. So this is t squared times an extra t, that's t cubed. Okay, so it's a partial of w with respect to x in terms of t. Now I want the partial of w with respect to y. Now this is also constant times y. The derivative of a constant times y is just the constant. In this case, the constant is x times cosine of z. And we want that in terms of t, so we replace x with x of t and z with z of t. X as a function of t was t. Z is arc cosine of t. So this ends up being the arc cosine, or the cosine of the arc cosine. Those just undo each other and you just get what's inside. That's t, because they're inverse functions. And t times t is t squared. Okay, so that's the partial of w with respect to y in terms of t. Now we need the partial of w with respect to z. Now I've got a constant times cosine of z. The derivative of a constant times cosine of z with respect to z is the constant, so that's the xy, times the derivative of cosine of z. The derivative of cosine of z is negative sine of z. Now this one is a little more challenging to simplify, but we'll simplify it. Maybe we'll simplify it in a little bit. Let's simplify it later. So I have negative x times y times sine of z, and I'm replacing x with t, y is t squared, and z is arc cosine of t. The sine of the arc cosine of t, that needs a little bit of simplification. But now I've got negative t cubed times the sine of the arc cosine of t. And we'll work through what that is in a little bit. So we found these three partials in terms of t. So we've got this guy, and this guy. Now I just need the derivative of x with respect to t, the derivative of y with respect to t, and the derivative of z with respect to t. I'm going to call those x prime, y prime, and z prime because it's shorter. So for this part, I take my x of t, which is just t. Derivative of t is 1. Take y of t, which was t squared. Derivative of t squared is 2t. So I bring my power down. I multiply by t to the 1 less power. Z of t is arc cosine of t. This may be one that you've forgotten. The derivative of arc cosine of t looks a lot like the derivative of arc sine of t. Arc sine is 1 over the square root of 1 minus your variable squared, which in this case is t, not x. That's the derivative of arc sine. Derivative of arc cosine is that times negative 1. Okay, so we computed those, and then we want to put all of those pieces together to find z prime, or w prime. Now, if you don't know what the answer already is, you might just leave this sine of arc cosine of t and not simplify it. But we know what the answer is. So maybe we want to simplify that. dw dt is partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt plus the partial of w with respect to z times dz dt. These parentheses aren't necessary. I don't know why I wrote them. I think I wrote them because I'm thinking of the next step when I'm going to be substituting in all of these parentheses. So let's write that next step down. So I'm here. I need the partial of w with respect to x. Well, from earlier, partial of w with respect to x in terms of t was t cubed. And the derivative of x with respect to t, that's the same as x prime, that's 1. And then the partial of w with respect to y in terms of t Well, from earlier, that was t squared. And I'm multiplying that by the derivative of y with respect to t, which is 2t. And then I'm adding partial of w with respect to z, which is the most involved looking because it doesn't look like it simplifies, but it does. I've got negative t cubed times the sine of the arc cosine of t. I'm sorry, that's very small and difficult to read. I'll write that bigger on the next line. Times dz dt, which is this. Oops, I should have done that in red. That's okay. All right, so we end up with t cubed plus 2t cubed, a minus, it's going to be a plus, t cubed times the sine of the arc cosine of t, all divided by the square root of 1 minus t squared. And all of this is dw dt, or if you prefer, it's w prime. And of course, we can simplify the like terms here. I've got 2 of these, and I've got 1 more, so that's 3 of them. You might say, how on earth do you simplify that? Well, arc cosine of t is an angle. So I'll draw a little triangle. I'm going to call that angle theta. If arc cosine of t is theta, then when I take the cosine of both sides of this, the arc cosine and the cosine undo each other, and we just have t has to be cosine of theta. So cosine of theta, which we know from SOHCAHTOA is adjacent over hypotenuse, has to be t over 1. So that ratio of the adjacent side to the hypotenuse is t divided by 1. And then using the Pythagorean theorem, this squared plus this squared has to be this squared. If you use the Pythagorean theorem, you'll find that that's our third side. So arc cosine of t is theta. Now I want sine of theta. Well, I can use this triangle to find sine of theta. Well, sine of theta, using SOHCAHTOA again, is opposite over hypotenuse. So that's square root of 1 minus t squared over 1. What does that mean? That means this is the square root of 1 minus t squared. So these guys reduce, because they're exactly the same thing, and we end up with 3t cubed plus another t cubed, that's 4t cubed. And that's exactly what we got using the other method, which was much faster and simpler. Okay, but we wanted to show that we know how to use the chain rule. So that is our chain rule. For a function of 3 variables, it has 3 terms, and you're going to get the exact same answer that you would get if you replaced x with x of t, y with y of t, z with z of t, and then just took the derivative that resulted. Now we could also do exactly the same thing using the gradient. Now I'm not going to do it again, but I just want to show you this is the same as the partial of w with respect to x times I hat plus the partial of w with respect to y plus the partial of w with respect to z. It's that dotted with this. This is just another way of writing this, because I'm doing this times this, plus this times this, plus this times this. I get this. Well, that's the gradient of capital F, evaluated at x of t, y of t, z of t. And that is r prime. So if I dot these,